Okay, welcome everyone. We have here the Chapter 20 worksheet, which I'll go over. Uh, just by way of review, it's starting with some of these drawing compounds type questions. I will confess the secondary amine and the alpha beta unsaturated ketone are a little more relevant to Chapter 19 than Chapter 20, but any review is good review. So if you're asked to draw a secondary amine, I think that's a completely reasonable question. You need to know what an amine is. You need to know what primary, secondary, and tertiary amines are, along with quaternary ammonium salts. So a secondary amine is just an amine with two alkyl carbons attached and one hydrogen attached. So it's of the type R2NH. And I could imagine any number of correct answers. Probably the most obvious one is diethylamine, which looks like this, but an amine with one methyl group and one propyl group or isopropyl group would also be fine. That's certainly also correct. And an answer that probably not too many people would think of, but would be absolutely acceptable, would be peroxidine. That's a cyclic secondary amine with four carbons, with exactly four carbons. So there are other correct answers as well, besides these three. An alpha beta unsaturated ketone with exactly five carbons. So remember the definition of an alpha beta unsaturated ketone is, or an alpha beta unsaturated carbonyl compound of any kind, is that it has a carbon-carbon double bond conjugated to the carbon-oxygen double bond. And so again, the most obvious answer, the one I would expect that most students would put in answer to this question, would look something like this. We would have our ketone over here and our carbon-carbon double bond over here, but that's certainly not the only correct answer. If you wanted to move that down the chain, and come up with something like this. This would also be completely acceptable. I could imagine cyclic answers. Again, you can incorporate the five carbons into a ring and maybe do something like this. So don't be afraid of more creative answers like that. They're equally acceptable, obviously, as long as you follow all the rules of structure drawing and you do what the problem says. So all of those are correct. A nitrile with exactly five carbons. Nitriles are part of Chapter 20. So again, the most obvious solution, and the one, I don't know which year I asked or semester when I asked this question on an exam, but I would bet you that of the people who got the right answer, nearly all of them put this answer, but there's many other correct answers. I could imagine something like this. One, two, three, four, five. Of course, remember, the nitrile carbon is included in the carbon count, so this would be absolutely acceptable. Totally correct. Good. So let's move on then. We have a couple of reaction questions over here. And here we need to put in just one structure, exactly one structure corresponding to the single major organic product. Should always be a neutral molecule. The first reaction is reduction of a nitrile with lithium aluminum hydride, followed by an aqueous acid workup. And as I speak, we're going to go over this tomorrow in class. But nitriles get reduced by lithium aluminum hydride to form the corresponding primary amine, which would look like this. It is the same number of carbons. Naturally, that's not the only correct way to draw it, but that would be the correct answer. And the next question has, again, an LAH reduction of a carboxylic acid, and you need to know that carboxylic acids get reduced by LAH to form the corresponding primary alcohol. LAH is not the only reagent you'll need to know about from chapter 20, but these are some characteristic types of questions. Remember that you do need LAH to reduce a carboxylic acid or an ester. Sodium borohydride will not touch these compounds. They're not strong enough. It's not a strong enough reducing agent. But LAH will reduce a carboxylic acid or an ester to the corresponding primary alcohol, corresponding meaning that it has the same number of carbons in the chain. And likewise, LAH will reduce a nitrile to the corresponding primary amine. And if you wanted to look at another way of drawing that compound, you could certainly just use a line angle drawing like this. Absolutely equivalent structure. Either way is completely fine. They are both equally correct, equally acceptable. So, so much for those questions. We also had a couple of mechanisms. There are not that many reactions in chapter 20, but a couple of them, these are not the only ones, but a couple of them include this type of reaction. Here we're given a carboxylic acid. We're treating it with base. This could say NaOH also. It could just say OH minus also. They're all equivalent reagents, as you know. They're all sources of the hydroxide ion, followed by treating it with phenethyl bromide and resulting in this ester over here. So this is a reaction that we will have talked about. Again, as I speak, I plan to talk about it in class tomorrow, but this reaction starts by deprotonating the carboxylic acid with a base, and you don't even need to go as far as hydroxide. Weaker bases than hydroxide will also work because carboxylic acids are pretty acidic. So if this had been sodium bicarbonate, for example, NaHCO3, that would also easily deprotonate the carboxylic acid to give the conjugate base, the carboxylate ion, which we talked heavily about conjugate bases of various acids in yesterday's class. So in the first step, you would need to show hydroxide pulling off that proton, reaching out with an electron pair from the hydroxide oxygen towards the carboxylic acid hydrogen. And then you need to show breakage of the oxygen-hydrogen bond and pushing the electrons onto the carboxylic acid oxygen. So notice that I've not written K plus anywhere. I've not shown a potassium-oxygen bond. Remember, metals don't form covalent bonds with oxygen. So we don't even acknowledge the potassium ion. It plays no role in the reaction. It's just a spectator ion. Anyway, that gives us the carboxylate ion. This will then undergo an SN2 reaction with this primary alkyl halide. I expect you still to remember the mechanism of a typical SN2 reaction, and this would certainly be one of them. This is no different from what you discussed last semester in chapter 11. So you show electrons coming from the carboxylate oxygen with the minus charge pointing towards the carbon that bears the leaving group. Always point your nucleophile arrow towards the carbon that bears the leaving group. You break the carbon-halogen bond, and you get the ester. And this is one way of making esters. It's not the most common way. Certainly, it's not the most common way if you wanted to just make an ethyl or methyl ester. Then you would probably use something called a Fischer esterification, which we will discuss in chapter 21. But this is also a very clean, very efficient way of making an ester. And if I were wanting to make an ester other than a methyl or ethyl ester, I would probably use a reaction like this. It should be very clean and high yielding. And then we have the reaction of a Grignard reagent This could also have been an alkyl lithium, so it could have said Li instead of MgBr. The result of the reaction and the mechanism would be exactly the same. We're treating the Grignard reagent with carbon dioxide. In fact, I believe you're doing this in lab, followed by an aqueous acid workup, and the resulting product is the carboxylic acid with one extra carbon. So it's the chain extended carboxylic acid. And the mechanism goes by attack of the Grignard reagent onto carbon dioxide. So I do expect you to know the structure of carbon dioxide. You show the electrons in the carbon metal bond. And again, if this were Li instead of MgBr, it would be exactly the exact same arrow, starting and ending at the exact same place. The arrow ends at the carbon dioxide carbon. That carbon is strongly electrophilic. It's basically like a double carbonyl. So carbon dioxide is a very good electrophile. We then break one of the carbon-oxygen pi bonds. It doesn't matter which one, they're the same. And that gives us this carboxylate ion. So we've just formed this carbon-carbon bond over here. And then in the second step, we add aqueous acid. So we draw a hydronium ion and we show the electrons on the carboxylate oxygen reaching out to grab a proton off of the hydronium ion. We break the oxygen-hydrogen bond, push the electrons onto oxygen to make a neutral water molecule, and that converts the carboxylate ion to the free carboxylic acid. So again, that's about it for this one. These are not the only reactions in chapter 20, but candidly, there are not many reactions in chapter 20. There are far, far more in chapters 19 and 21. So this at least is a concise review of some of the topics that we covered in chapter 20. We also talked about comparing relative acidities of carboxylic acids given their pKa's and understanding why the trend is what it is. That was mainly our class topic yesterday. So that's another topic that's fair game for chapter 20. Other than that, I think I'll leave that here. This video looks like it'll only be about 15 minutes. That's a record short one, but again, there's not as much to cover in chapter 20. And I expect the next video that we make for chapter 27 on lipids will likewise be short. So we'll leave it there for today. Have a great day. I will see you all in the next class.